Hey, what's up, guys? Yeah, so today I want to talk about irrationality and the Liouville number. Also, this video is almost the same as the previous one, but I want to introduce the idea of this Liouville number. Okay, so Liouville number. Sometimes are hard to pronounce this. Hopefully, my pronunciation is correct. Hope you guys subscribe to my channel. Okay, so definition. So the Liouville number basically is a real number x, such that what? For every positive integer n, then there is a pq. They are both integer. So both integer such that the q greater than 1. And we have x minus p divided by q, the absolute value less than 1 over q to the n. Okay, so this is numbers really very rational. Okay, so this is called Liouville number. Okay, and I will briefly review the proof of the Liouville approximation theorem. But what I'm saying is that the theorem is basically the following. So the Liouville number is transcendental. So basically, these numbers like very like man-made it, so that it's like very tricky that these guys these guys are transcendental. So remember is that for every n such that these are true. Okay. Okay, so before we start, let's prove a very simple thing, which is so simple. Okay, so theorem. Okay, so theorem says that such a number must be irrational. Okay, so proof is like very simple, right? We want to show that it cannot be rational. So so the proof is very simple. Let's just let's do this, right? So let's say x is rational, so c divided by d, and d is greater than 0, and suppose CD are coprime to each other, so CD are coprime. Okay, so we can let's just pick n such that 2 to the n minus 1 is greater than d. Okay, and we want to say that we want to claim that there's no PQ, such that so we want to prove the contradiction, right? So we want to prove that there's no PQ such that x minus p divided by q is less than 1 over q to the n. We want to say that this is never true. Okay, so this is never true. Okay, so this the proof is very simple. So suppose such PQ exists, right? Suppose such PQ exists, then let me just compute x divided by minus p divided by q. So I can write c divided by d minus p divided by q. So I absolute value, then I get the dq cq minus pd, take absolute value. And okay, so if cq minus pd is 0, then it's not suitable, right? Because it's, I mean, if it's 0, that means that it violate the first we violate this term, right? So cq minus pd cannot be 0, right? Otherwise our proof is our proof is invalid. Okay, so we must demand that CD this CQ minus PD is non-zero. Okay, so that means we can assume that CQ minus PD is greater than 0. Alright, so it's integer, so it must greater or equal to 1. Okay, but then this guy will greater than 1 over dq. Okay. But by my assumption is that 2 to the n minus 1 greater than d, right? So this guy must greater or equal to 2n minus 1 q, right? So it must be greater or equal to 1 over q to the n, because my assumption, right, d is less than 2 to the n minus 1. And let's see, I should consider something. Okay. Okay, right, yeah. So 2 to the n minus 1, q must greater or equal to q to the n, right? Because q greater than 1. Okay. By definition, right? Because q greater than 1. Okay, so that means that this proof that this such number must be irrational. Okay, so now let's claim that this Liouville number must be transcendental. Okay, so in order to prove it is true, we need to use the quickly says this Liouville approximation theorem. Okay, so this theorem, let me just recover it again. So basically, you consider alpha is irrational, and but alpha is algebraic, right? So suppose there exists the f which is irreducible. Let's say I think over q, so f alpha is 0, and let's say degree f is n greater or equal to 1, and let's say it's greater or equal to 2. Okay, then there exists a which is a constant real number such that for all pq, for integer pq, q greater than 0, we have, so basically algebraic number can be approximate, right, by this cannot be approximate so well. Okay, so algebraic number cannot be approximate so well means that alpha minus p divided by q must greater or equal to 1 over q to the n. There's an a here. Okay. Okay, so I think previously I gave one proof, right? This time I gave a similar proof, but maybe it's more elegant. Okay. So proof is very simple. Let's consider so this proof may be simple. Let's consider m to be the maximum value of f prime of x over interval. Okay, so let's consider this. So let's consider mx of the derivative absolute value, and then consider x belongs to, let's say, alpha minus 1 and alpha plus 1. Now let's assume alpha is real. Okay, and okay, and we know that f alpha is 0. Okay, so I can say that alpha 1, alpha 2 up to alpha m are all are distinct roots different from alpha. Distinct roots different from alpha. Okay, so since they are irreducible, right? So this should not have the multiple roots. Okay, and then we take a. So this is a very beautiful. We take a to be the minimum, less than minimum of 1 over m, and alpha minus alpha 1, alpha minus alpha 2, and up to alpha minus alpha m. Okay. Okay, so let's see. So let's say alpha minus p divided by q. Okay, so that's proved by contradiction, right? Suppose there is a PQ contradicts our results. Suppose there are PQ contradicts our claim. That means that alpha minus PQ will less than equal to a q to the n, right? Since q greater than 1, so less than equal to a, and then we're less than the minimum of this 1 over m, alpha minus alpha 1, alpha minus alpha 2, up to alpha minus alpha m. Okay, and okay, but please tell you what this, if there this PQ is this, right? Since they less than 1, right? So it means that alpha must belongs to, sorry, p divided by q must belongs to alpha minus 1, alpha plus 1, because there are less than 1, right? Okay, and we know that p divided by q is not the root of f, right? We know that p divided by q is not the root of f, because I mean f is irreducible there, so there should be no rational roots, and there's no roots, and also there's no roots. There's no roots between alpha and p over q, right? Because I already assumed this, they are very so small that smaller than every distinct roots, right? So so this p divided by q will not touch any roots. Okay, then we do the same thing like by the MVP mean value theorem. So we know that we are f alpha minus our f, right, p divided by q will be alpha minus p divided by q f prime of 0, f prime of x0, where x0 belongs to p divided by q or alpha, or maybe the other direction is alpha or p divided by q. Okay, so very simple calculation. We know that this is minus, let's write this. So let's write alpha minus p divided by q is f of alpha minus fp divided by q divided by f prime of x0. Okay. And we know that f alpha is 0, right? So we get the fp divided by q divided by f prime of x0. Okay. Okay. And the fp divided by q, very simple calculation. You just write down everything, right? So you know that this guy must be, you can prove, easily prove this is greater than 1 over q to the n. Okay, so let's prove that alpha minus b divided by q to the n will greater than equal to 1 divided by m more q to the n. Because I already assume that f prime, right? I already assume m is the upper bound, right, of this derivative. Okay, so we're greater than equal to a divided by q to the n, we're greater or equal to alpha minus p divided by q. Okay, so this is contradiction, right? Because alpha minus p divided by q is by definition, right, less or equal to, greater or equal to this, greater than this, by definition, satisfy this. Okay, so right, so the proof basically say that we want to collect, we suppose this is false, right? So you will get something maybe here. Sorry about this, you'll get something here. And that means that you can find the alpha minus p equal less than a divided by q to the n, right? So which give you this, right? But you from here you prove that you go to another direction, right? Then this contradicts your assumption. Okay, so that means that algebraic number cannot be approximated so well. Okay. Okay, so now we can prove the theorem says very simple. So the linear number is transcendental. The reason is very simple, right? Because the linear number doesn't satisfy this previous lemma. Okay. Because this linear number, because if x is algebraic, then this is always true, right? That means that there is always exists a, right, such that x minus p divided by q greater than a divided by q to n. So a is universal. So there is a universal a such that for every pq, for every relative prime, or for every q greater than 1, it always satisfies this. Okay. But my definition for the linear number says that for every n, then I can always find a p and q such that this guy less or equal to a divided by q to n. Or sorry, less or equal to this. Okay, so the linear number tell you this, right? So this tell me that for every n, then I can always find pq such that bounded by arbitrary n. Okay, but the linear number doesn't satisfy the previous lemma. So then that means that this linear number must be transcendental by definition. Okay. Because for every n, you can always find pq such that it's less than 1 over q to the n. It doesn't satisfy this condition. Okay, okay, so see you guys next video. So next video I will prove the Hurwitz theorem, which is like the stronger version of the Dirichlet approximation theorem, and see you guys next videos.